Okay, in today's video we're going to try to turn some of the maths we did in the first video into some code and start moving this robot. If you haven't watched the first video, you won't know what all this maths is, so you'll have to go back and watch that first. Now, just a few little basics here. The PCB that controls all the servos on this robot is an ESP32, and I control it wirelessly from my computer, and it's all my software is programmed in MicroPython. Now, when I've wrote my drivers for controlling the servos, instead of it setting the servos in degrees, it sets it in radians. And I did this for a reason, because all trig functions in Python return radians, not degrees. Now, a quick little brush up on what's the difference between the two. So a radian is the distance around the circumference of a unit circle. So if we know that the circumference of a circle is 2 pi r. All right? So if we have r is 1, it'll be 2 pi times 1, which is 2 pi. So you know the outside of that circle is going to be 2 pi. So if you want 360 degrees, it'll be 2 pi. If you want 180 degrees, it's the distance around the circumference till you hit 180 degrees, which will be pi. If you want 90 degrees, of course going up to there will be half pi. If you want 45 degrees, instead of measuring it as 45 degrees there, we'll measure it by the distance going up there, which will be quarter pi. Right? And that's how radians work. They work by just measuring how far around the circumference of the circle you're going to go in a unit circle. And that's how a lot of high mass functions work. Now, I'm not going to worry too much about my code at the top. What you really need to know is what's happening down here. Right, this here's how I set the angles. So I'm using body position 0, which just means the first leg. If I use 1, 2 or 3, it will use one of the other legs. And then I give it 3 numbers. At the moment, it's 0, 0, 0. So that means I wanted it to set all the servos at position 0. And that's what you see there. So the top leg is square out, the next arm comes straight out, and the next leg comes straight down. So that's my 0, 0, 0 position. If I go here and I say change this second one here to pi divided by 4, which is 45 degrees, and I save that. Let's get the save. She's downloaded, and then I hit run, enter. It moves up by a quarter pi, which is 45 degrees by the middle leg. If I come back to here now, and I turn that back to 0, and I make this one pi by 4, and save, download, cool, switch back, now we're going to run. So it puts that one back to 0 and that one out to 45 degrees, right, or quarter pi. Alright, so you can see, and if I would have changed the very, very first one, which I left at 0, it would shift that one. But for the moment, we're only doing these two here. So you can see I can just simply tell in my software which leg I want and what radians I want each servo at, and then I tell it update and it sends it to the servos. Alright, that's the main thing you need to know. Okay, some very quick revision. We're trying to work out our two angles, theta 4 and theta 3. That's the formulas there for them. To work those out, we need to know what T1 and T2 is. That's the formula for T1. Right? To work out T1, we need to know what L is. That's the formula we worked out for finding L. Right? Once we know T1 and L, we can work out T2 with that formula, and then we can substitute them back into that, and boom, we have our angles. The very first thing we need to do is work out L. L's the hypotenuse of Z and X in that triangle there. And that's the formula for doing it. Instead of having to write out that whole formula, Python actually has a built-in function to do that. L equals hypot xz, already done. Then the next formula I need to put in is to calculate T1, which is that formula there. So you can see going in here, the exact same one, T equals L squared minus A squared plus A1 squared all over 2L, right? Then we can calculate T2 from our formula here. He goes into there, into the next line of code. And once we've done that, we can calculate theta 4 and theta 3 with these two formulas. Boom, there they are there. So that's a nice little subroutine I've wrote to calculate those two angles. Now I've made a for loop down here that cycles through x in the range of 30 to 100. So it'll make it 30, and then I'll go through 31, 32, 33, cycle right through between 30 and 100. And I'm going to set that body position to that, right, calculate out the angles, and then update it. So that should just make the foot move between 30 millimeters out to 100 millimeters out, keeping it 50 millimeters down. All right, so we can say, okay, run program. I come into focus. It's just moving him out 1 millimeter, updating and moving him out 1 millimeter, updating him. Now you notice it's running very, very slowly. And that's because of how heavy our mass is. Right? We need to make our routine a little bit more efficient. Okay, now looking for some efficiencies we can do. Now A2 is always going to be the same, so the square of A2 is going to be the same. A1 is always going to be the same, so the square is going to be the same. So each loop around, we don't actually need to do this calculation. We can actually just work it out and put a number in here, and that will save squaring both of those and adding those together. Right, now, also on top of that, we're writing A here, and we have the variable up here, which means it has to look it up and transfer it across. If we write those actual numbers in there, that will help speed that up. Also here we're doing pi divided by 2, which is another floating point mass, which we don't need to do. We can actually just physically calculate out what that value is and put the minus the value there, and that will reduce the amount of calculations involved in running that a little routine and help it to run a bit quicker. Okay, so I've gone and implemented those few changes, put some constants in there, so there's a little bit less calculating going on. I also noticed my time sleep before was actually quite long, and that's what was slowing it down a bit. So I've changed it to 10 milliseconds now, so there's only a tiny little sleep there. Right, so I'll switch back to my program, hit run. Yeah, he runs out, no worries. So we've got that bit going nicely now. Now another little note, if I want it to move quite quick, instead of stepping at 1 millimeter at a time, I've now changed to step 3 millimeters at a time. Right, so if I switch over now and run this program, you ready? You see it moves quite quickly because it's now stepping 3 millimeters at a time instead of 1 millimeter at a time. So I can change the speed of my robot depending how big a step I want to take on each update, whether I want to just move 1 millimeter on each update or I want to move 3 millimeters on each update. Okay, I've changed it back just to move 1 millimeter at a time, so it moves nice and slow and you guys can see what's going to happen. But before I had it moving between 30 millimeters and 100 millimeters. I've changed it now to 150 millimeters, which is further than what my spider leg can reach. So now I'm going to ask it to place its foot where it can't actually physically reach its foot. Go back and we hit run program now. When it gets out to there, my program crashes because it says the maths are no longer calculatable. Okay, this mass error is going to happen anytime I make Z and X so big that L becomes longer than what the length of the two arms are together. Alright, so anytime that A plus A1 is smaller than what L is, I'm going to get that error. So what I need to do is I need to calculate L. Once I've calculated L, check that L is smaller than A1 plus A2 before calculating the rest. Now if it's not, what we're going to do is excuse me, we're going to make the leg totally straight. So that joint will be at 180 degrees out in a straight line. And then what we want to do is we want to point this angle to point in the same direction as L. So what we will need to do is we will need to set this angle here to negative theta 5. And we know that theta 5 is tan z over x. Okay, here's my code with the error checking. The first thing I do is I calculate L. I check that L is smaller than those two added together. Just highlighted there. If it is, I just do exactly what I was doing before. If it's not, then I say I set theta 3 to sticking straight out, and I set theta 4 to the negative of a tan z over x. So now we'll run this routine and we'll see what we get. Focuses. Now he sits there, he pushes him out in a straight line, pushes him out, pushing him out, pushing him out, pushing him out. Once he gets past what he can reach, although the destination gets further and further, he just keeps pointing at his foot at that further and further destination without any mass errors. Right? Went all the way out to where he exactly should do. Okay, in order for these videos not to get too long, we'll pull this one up, and we seem to have those two joints working very well now. We can control speed of them, and we can also have error checking if we give it a position outside what it can reach. So the very next thing what we're going to do is, in the next video, we're going to look at how to add on this last joint we haven't done. All right, but I'll save that for the next video.